Hello learners, on behalf of Indira Gandhi National Open University, we welcome to this video lecture session. Today's topic is Introduction to Refrigeration System. This topic is 35th module of the course Thermodynamics and its application. I am Subhashish Maji, professor in School of Engineering and Technology from Indira Gandhi National Open University. Dear learners, let us begin our discussion. After listening to this video lecture, you will be able to understand the refrigeration system, you will be able to know refrigerator and heat pump, you will be able to describe the Carnot refrigeration cycle, you will be able to explain the capacity of refrigerator, and you will also be able to calculate the coefficient of performance of a refrigerator and a heat pump. Creation of a temperature below normal temperature has been established as a need of human being. There are two reasons for it. Firstly, there are eatables which do not last long at normal temperature but survive at sufficiently low temperature. Secondly, at many geographical locations, the atmospheric temperature is too high to make living and working comfortable. When man becomes capable of creating low temperature, then arose many other needs that could be satisfied by such devices. Refrigeration is commonly used to preserve food over days in homes, over months in cold storage, for supplying cold water and beverages, for storing medicine in stores and in homes, and many more things. The same devices can be used in industry for preservation of chemicals and intermediary products. In medical practices, the device of low temperature are used to preserve samples of blood, etc. for the period of testing. Space cooling and maintaining certain air quality and circulation became the byproduct of low temperature creation. This practice is known as air conditioning and covers not only cooling of air but also maintaining moisture, order and speed of circulation in closed space. Like refrigeration, air conditioning also has found its use both in house and industry, and with human beings spending sufficient time in travel, air conditioning has become an important component in automobiles, trains, ships and aeroplanes. Now let us discuss about the methods of refrigeration. There are different methods of refrigeration, like refrigeration by non-cyclic methods, refrigeration by using ice or snow, refrigeration by evaporation, refrigeration by cyclic methods or by means of mechanical or artificial systems, as by using non-condensable gases such as air, carbon dioxide and sulfur dioxide. Second one, by using condensable vapors. Vapor compression refrigeration systems and vapor absorption refrigeration systems are widely used for the refrigeration process. There are other methods of refrigeration like magnetic refrigeration system, vortex tube system, thermoelectric refrigeration system, steam jet refrigeration system, ultrasound refrigeration. There are natural methods for refrigeration. One is by using ice or snow. Second one is evaporative cooling process or adiabatic cooling process. Let us discuss about the refrigeration system by using ice or snow. The natural method include the utilization of ice or snow produced naturally in cold climate. Ice melts at 0 degrees centigrade, so when it is placed in a space or system warmer than 0 degrees centigrade, heat flows into ice and the space is cooled. The ice melts into water by absorbing its latent heat at the rate of 335 kJ per kg. The river water, if it is quite cold, may also be used for cooling certain systems, but the removal of heat will not be as fast and satisfactory as in the case when ice or snow is used. The natural methods of refrigeration were actually used in early days. With the present development in science and technology and the subsequent rise in the standard of living, the refrigeration requirements have become so large that the natural methods have become inadequate and therefore obsolete. When ice is to be used for refrigeration, winter ice can be stored by packing it in straw and dried weeds for use in the summer months. Evaporative cooling process or adiabatic cooling process. In the older days, it was observed by the people that evaporation of water naturally causes cooling effect, and hence they used to put their wine or other liquids into porous earthenware containers placed in the open atmosphere such as roof. We have everyday experience that water kept in an earthen pot becomes cooled because of the evaporation of water absorbing latent heat of evaporation from water in the pot and coming out through the pores. This effect is experienced very well in summer. Air flowing over the surface water whose temperature is less than the incoming air, then air is cooled because of the evaporation, during which latent heat is taken from air and water sum. Evaporation of sweat on our body, thereby producing cooling effect, is the best example of evaporative cooling. Refrigeration is the process of maintaining a body or a zone in space at a temperature lower than the local surrounding temperature. Hence, refrigeration requires the continuous transfer of heat from the body or the zone to be refrigerated to the surrounding at a relatively high temperature. It has been explained in our earlier discussion that such a job can be done by a reverse heat engine, a refrigerator. However, this is not the only method available for providing refrigeration. There are several other methods used in practice. The most commonly used methods are vapor compression refrigeration system, gas compression refrigeration system, and vapor absorption refrigeration system. Now let us see this diagram. The left one is direct heat engine, where Q1 is the heat extracted from a source whose temperature is T1. The engine takes the heat, does work W, and the Q heat is rejected to the sink, and you must remember that the temperature of source T1 is always greater than the temperature of sink T2. But the reverse heat engine, if you want to transfer the heat from a low temperature region to a high temperature region, we must do work that is done in the reverse heat engine. W is the work done on the reverse heat engine to extract heat Q2 from a low temperature region and transfer it, the heat Q1, to the high temperature region whose temperature is T1. Coefficient of performance. Coefficient of performance, in short we will say COP. COP of a refrigeration system is defined as the ratio of heat extracted in a given time, that is known as the refrigeration effect, to the work input to the system. So, coefficient of refrigeration is equal to heat extracted divided by work done. We can also say COP is equal to net refrigerating effect divided by compressor work. Now let us see what are the applications of refrigeration. For preserving fresh food, we can use refrigerator. To store medicine, vaccine, blood plasma, to store cut flowers, for preserving it for longer period, we use refrigerator. Ice plants use refrigeration machine. Industries use refrigeration for producing frozen fruit, juice, ice cream, chemicals. Manufacturing industries use refrigeration. Refrigeration is used for cutting oil to remove wax in oil refineries. Now let us discuss the capacity of a refrigerator. It is the rate at which heat can be extracted from cold body, the rate at which refrigeration can be produced. It is defined as the quantity of heat removed to freeze 1 ton of water at 0 degree centigrade to ice at 0 degree centigrade in 24 hours. So 1 ton of refrigeration is equal to 12. So 1 ton of refrigeration is equivalent to 12,600 kilojoule per hour. That is also equal to 210 kilojoule per minute. That is also equal to 3.5 kilojoule per second. Refrigeration can be easily regarded as reverse process of an engine. Carnot cycle is a reversible cycle and hence can be used as a refrigeration cycle. The figure 2 shows the PV diagram, that is pressure volume diagram of a reversed Carnot cycle. A refrigeration system removes heat from a low temperature region and transfers heat to a high temperature region. The Carnot cycle can serve as the model of the ideal refrigeration cycle, considering all refrigerators operating between the same two thermal reservoirs. The maximum coefficient of performance is attained by the Carnot refrigeration cycle. This is the pressure volume diagram of reversed Carnot cycle. So 1 to 2 is adiabatic expansion, 2 to 3 is isothermal expansion, and 3 to 4 is again adiabatic process, and 4 to 1 is also isothermal compression process. Air in space of cylinder is expanded adiabatically from 1 to 2, reducing temperature from T1 to T2. It is further expanded isothermally, and during this expansion, heat is absorbed from colder body at temperature T2. The air then compressed adiabatically in the cylinder, for which work is supplied from outside. The temperature of water rises from T2 to T1. Finally, air is isothermally compressed to pressure P1. That completes the cycle. Heat removed from colder body during isothermal process, that is 2 to 3. This heat is Q23 is equal to RT2 ln V1 by V2. The heated and compressed air rejects heat at T1 to the hot body during isothermal compression from state 4 to state 1. That is equal to Q41 is equal to RT1 ln V4 by V1. The work supplied is the difference of these two heats, that is Q41 minus Q23. The refrigeration effect is the heat removed from colder body, that is Q23. The coefficient of performance of a refrigeration system is defined as the ratio of refrigerating effect by mechanical work. So from this we can get the expression for the coefficient of performance for the refrigerator, that is equal to Q23 divided by WC. So Q23 is net refrigerating effect and WC is the work done by the temperature. That is equal to Q23 divided by Q41 minus Q23. If you put the values of Q23 and Q41 and do the little algebra, you will get the final expression for coefficient of performance for refrigerator, that is equal to T2 divided by T1 minus T2, but we have to note that the ratio of V3 and V2, that is V3 by V2, is equal to V4 by V1. Now let us discuss about the heat pump. A refrigerator provides a low temperature region by transferring continuously the heat from the region to be cooled to the surrounding at a relatively high temperature. A refrigerator or a window air conditioner, which also operates on a cycle similar to that of the domestic refrigerator, is a necessity in hot climates. In cold climates, it may be necessary to provide a relatively high temperature region like a heated room. This can be achieved by a heat pump whose operations is exactly similar to that of a refrigerator. Figure 1 is also schematic of a heat pump. In a heat pump, one is interested in Q1, the heat transfer to the high temperature region. To maintain the high temperature region, heat is continuously transferred to it from the low temperature surrounding with the help of work supplied to the compressor. It may be imagined that a domestic refrigerator can be used as a heat pump by installing it in such a manner that with its door open, the cabinet to exposed to the cold weather outside the room and the condenser coil is exposed to the room air to be heated. It is needless to mention again that a heat pump is also a work absorbing cycle. So the coefficient of heat pump is equal to Q1 divided by WC. We can also write this equal to Q1 divided by Q1 minus Q2. If you do little algebra, you will find that coefficient of heat pump is equal to 1 plus coefficient of refrigerator. Now let us talk about the air conditioning system. The process of conditioning the surrounding air according to the human comfort and desire is called as air conditioning system. We all know the purpose of air conditioning system, like restaurants, hotels, home, hospitals, airplanes, offices, etc., where we have seen that air conditioning system is must nowadays. Air conditioning helps control moisture in printing press, in business and industry. Air conditioning improves efficiency, manufacturing of tools and instruments, textile mills, where air conditioning systems is absolutely necessary to maintain the moisture in the process control systems, and also air conditioning systems is very much required in pharmaceutical, chemical plant and food industries. Now let us discuss some very interesting numerical. The exercise 1. A reverse heat engine is operating between -10 degrees centigrade and 40 degrees centigrade. Find the COP as heat pump and refrigerator. But we know very well the expression for COP of refrigerator is equal to T2 divided by T1 minus T2, where T1 is the temperature of the source and T2 is the temperature of sink, but in this case the lower temperature is T2 and the environment temperature is T1. T2 is given as minus 10 degrees centigrade, T1 is given as 40 degrees centigrade. Just put these values in the expressions of COP of refrigerator. But dear students, please be careful while putting these values in the expression. Before that, we have to convert it in Kelvin scale. So T2 is minus 10 degrees centigrade is equal to 263 Kelvin, and T1 is given as 40 degrees centigrade is equal to 313 Kelvin, and you will get the COP of refrigerator is equal to 5.26. But COP of heat pump, we know that it is 1 plus COP of refrigerator, so COP of heat pump is equal to 6.26. Assume that the efficiency of the heat engine as shown in the figure is 40%. If this engine operates as a refrigerator between the same two temperatures with the same magnitude of heat and work interactions, what would be its COP be? We know very well that efficiency of the engine, that is equal to 40%, that is 0.4. Just put this value of efficiency in the expressions for the efficiency of a heat engine. In this case, the Carnot efficiency is equal to T1 minus T2 divided by T1, that is given as 0.4. Put the value, you will get T2 is equal to 0.6 T1, but coefficient of refrigerator is T2 divided by T1 minus T2. Put the value of T2 as 0.6 T1. Then finally you will get the coefficient of performance of refrigerator is equal to 1.5. Exercise 3. A refrigerator with COP of 2.5 transfers heat at a rate of 0.7 kJ per second at the condenser. Find the rate of heat transfer at the evaporator and the power input of the compressor. Also calculate the COP if the refrigerator were to operate as a heat pump with same heat and work interactions. Dear learners, while solving any numerical on thermodynamics, first you note down the data given for a particular numerical. Then things will be very much easy for solving any problem on thermodynamics. So COP of a refrigerator, we know very well it is equal to Q2 by WC. So Q2 is equal to 2.5 WC. So Q1 minus Q2 is equal to WC. See the diagram and apply the first law of thermodynamics, you will get this expression. So WC is equal to 0.7 minus 2.5 WC. Finally you will get WC is equal to 0.2 kJ per second. So Q2 is equal to 0.5 kJ per second, and the coefficient of heat pump is equal to 1 plus coefficient of refrigerator, that is equal to 1 plus 2 divided by WC. So COP of heat pump is equal to 1 plus 2.5 is equal to 3.5. The next problem, a domestic food freezer maintains a temperature of minus 13 degrees centigrade. The ambient temperature is 35 degrees centigrade. The heat leaks into the freezer at a continuous rate of 2 kJ per second. Calculate the least power required to pump this heat out continuously. You see the refrigerator, W is the work done onto the system for extracting heat Q2 from a low temperature region and rejecting this heat Q1 to the high temperature region. We know very well the coefficient of performance of a refrigerator is equal to net refrigerating effect divided by W, that is equal to Q2 divided by T1 minus Q2, that is equal to T2 divided by T1 minus T2. Put the value of T1 and T2 in the expression and finally you will get the work required equal to 0.37 kilowatt. Now we have concluded our today's discussion. Now let us summarize our discussion very quickly. In this lecture session, we have discussed the refrigeration system, we have discussed the refrigerator and heat pump, we have also discussed Carnot refrigeration cycle, we have also discussed the capacity of refrigerator, and finally we have solved some interesting problem to calculate the coefficient of performance of refrigerator and heat pump. Thank you.